Welcome to this problem-solving session. Today, we'll be diving into problem number 1615, titled Maximal Network Rank. In this problem, we'll analyze how to calculate the maximum network rank between cities in a graph. Let's explore the intuition, approaches, and optimizations to solve this problem efficiently. In this problem, we are working with an undirected graph that consists of n nodes, labeled from 0 to n1. The graph is described using a 2D array called roads. Each element in this array, roads, I, equals A underscore I, B underscore I, represents a road that connects two nodes, A underscore I and B underscore I, in a bidirectional way. Now, the concept of network rank comes into play. The network rank of two distinct nodes, say A and B, is defined as the total number of roads connected to either A or B. But there's an important detail: if a road is shared between the two nodes, it is only counted once in the total. Our goal is to calculate the maximal network rank, which is the highest network rank among all possible pairs of nodes in the graph. Let's look at an example to better understand this. In the first example, we have n equals 4 nodes in the following roads: 0, 1, 0, 3, 1, 2, 1, 3. This means there are 4 nodes labeled from 0 to 3, and these nodes are connected by 4 roads. For instance, node 0 is connected to nodes 1 and 3, and node 1 is connected to nodes 0, 2, and 3. By examining the connections, we can determine the network rank between different pairs of nodes. Continuing with the example, node 2 is connected to node 1, and node 3 is connected to nodes 0 and 1. Now, we calculate the network rank for all possible pairs of nodes. For example, for nodes 0 and 1, the total number of roads is 4, the roads connecting 0-1, 0-3, 1-2, and 1-3. For nodes 0 and 2, the total is 3, as we count the roads 0-1, 0-3, and 1-2. Similarly, we calculate for other pairs, such as 0 and 3, 1 and 2, and so on. After evaluating all pairs, we find that the highest network rank is 4. This is the maximal network rank for this graph. Let's examine another example to see how this works with a different graph. Here, we have n equals 5 nodes in the following roads: 0, 1, 0, 3, 1, 4, 2, 3, 2, 4. In this graph, node 0 is connected to nodes 1 and 3, node 1 to nodes 0 and 4, and so on. When we compute the network rank for each pair of nodes, we find that the pair 1, 4 achieves the highest total of 5 roads. This includes the roads 0-1, 1-4, 0-3, 2-3, and 2-4. Therefore, the maximal network rank in this case is 5. Finally, let's consider the constraints and edge cases for this problem. The number of nodes, n, ranges from 1 to 100, and the number of roads can be at most n*(n1/2, meaning there are no duplicate roads, and every road connects distinct nodes. For edge cases, if there are no roads, the maximal network rank is simply 0 because no connections exist. Similarly, if there is only one node, there are no pairs of nodes to compute a rank, so the result is also 0. On the other hand, in a fully connected graph where every node is connected to every other node, the maximal network rank depends on the pair of nodes with the highest combined degrees. These considerations are crucial for handling all possible scenarios in this problem. To solve this problem, we first consider a brute force approach. Here, the idea is straightforward: calculate the network rank for every possible pair of cities, I, J, and track the maximum rank found. The network rank of a pair is calculated as the sum of the degrees of the two cities, minus 1 if there's a direct road between them. Since a city's degree is simply the number of roads connected to it, we can pre-compute these degrees beforehand to make the computation more efficient during the pair evaluations. However, the trade-off with this approach is its inefficiency for large inputs. With n cities, there are n² pairs to evaluate, making the brute force method impractical for larger values of n. While simple to implement, this method scales poorly and is computationally expensive as the number of cities grows. This led us to consider a more optimized approach. The optimized approach builds on the intuition of the brute force method but significantly improves efficiency. By pre-computing the degrees of all cities, we eliminate redundant calculations during the pair evaluations. This pre-computation involves iterating through the list of roads and incrementing the degree count for the two cities connected by each road, which takes time, where m represents the number of roads. Next, we evaluate all pairs of cities to compute the network rank using the formula, the sum of their degrees, -1 if a direct road exists between them. Checking for the existence of a direct road is expedited using a set or an adjacency matrix, which allows 4O1 lookups. Although the overall time complexity remains O(n squared) due to the pair evaluations, the use of pre-computed degrees and efficient data structures ensures that the computation is significantly faster and avoids unnecessary overhead. Given the considerations, we chose the optimized approach as our final strategy due to its balance of simplicity and efficiency. While it retains a time complexity of O(n squared), the use of pre-computation and constant time operations for road existence checks minimizes redundant work and streamlines the process. This makes the approach well suited for the problem constraints. Pre-computing degrees ensures that we don't repeatedly calculate the number of connected roads for a city, while using a set or adjacency matrix provides an efficient way to verify direct connections. Additionally, the algorithm is straightforward to implement and debug, making it a practical and effective solution. Overall, this strategy achieves a good balance between performance and clarity, making it the ideal choice for solving the maximal network rank problem. To solve the maximal network rank problem, we first need to understand its components. The network rank for a pair of cities, denoted as I, J, is calculated as the sum of their degrees, the number of roads directly connected to each city, -1 if there is a direct road between the two cities. This subtraction ensures we don't overcount that shared road. To proceed, we start by representing the road network effectively. We'll use an array called degree where each index I corresponds to a city, and its value represents the number of roads connected to that city. Additionally, we need to track direct connections between cities. For this, either a set or an adjacency matrix can be used. A set allows us to store each road as a pair of connected cities, like I, J, while an adjacency matrix provides a grid-like structure where connected, I, J, indicates whether a direct road exists between cities I and J. These structures will enable efficient processing of the network data. Once the road network is represented, we move on to the calculation of network ranks. For every possible pair of cities, I, J, where I is less than J, we calculate their combined degree by summing degree, I, and degree, J. If there's a direct road between these cities, as determined from our set or adjacency matrix, we subtract 1 from the total to avoid double counting that road. At each step, we compare the current network rank with the maximum rank seen so far and update the maximum if necessary. After evaluating all possible pairs, the highest network rank we've tracked becomes our result, which we then return. Now, let's consider the key insights that make this algorithm efficient and accurate. First, the subtraction of 1 for direct roads avoids overcounting, which is essential for correctness. Second, because the roads are bidirectional, we only need to evaluate pairs I, J, where I is less than J, reducing redundant calculations. Lastly, the choice of data structures plays a crucial role. Using a degree array allows us to access the degree of any city in constant time, while a set or adjacency matrix provides an efficient way to check for direct connections. The degree array is compact, requiring space proportional to the number of cities, while the adjacency structures scale differently. An adjacency matrix uses O(n squared) space, but a set grows linearly with the number of roads, O(m). These design choices ensure that our algorithm remains efficient even as the input size grows. Analyzing the computational complexity, we see that building the degree array and adjacency structure takes O(m) time, where m is the number of roads. Calculating network ranks involves iterating over all possible city pairs, which takes O(n squared) time for n cities. Combining these, the overall time complexity is O(m plus n squared). For space, the degree array requires O(n), and the adjacency data uses either O(n squared) for a matrix or O(m) for a set. The choice of adjacency structure determines the overall space complexity. Special cases also need to be handled. If there are no roads, every network rank is 0. With a single city, there are no pairs to consider. In cases where all cities are fully connected, the algorithm must ensure direct roads are properly adjusted to avoid overcounting, maintaining correctness. To solidify our understanding, let's walk through an example. Suppose there are 4 cities and the roads are defined as 0, 1, 0, 2, 1, 2, 1, 3. First, we build the degree array, which results in 2, 3, 2, 1, representing the number of roads connected to each city. Next, we track the direct connections in a set 0, 1, 0, 2, 1, 2, 1, 3. Now, we calculate the network rank for each unique pair of cities. For the pair 0, 1, the rank is 2 plus 3 to 1, which equals 4. 4, 0, 2, it's 2 plus 2 to 1, giving 3. 4, 1, 2, it's 3 plus 2 to 1, again resulting in 4. Finally, 4, 1, 3, it's 3 plus 1 to 1, which equals 3. The maximum rank among these pairs is 4. Hence, the output is 4, representing the maximal network rank in this example. This Python implementation solves the LeetCode problem maximal network rank efficiently. The function maximal network rank takes an n, the number of cities, and roads, a list of directly connected roads between cities. The goal is to find the maximal network rank between any two cities. Explanation. 1. Initialization. A degree array degree is created to keep track of how many roads are connected to each city. A 2D list is _ connected serves as an adjacency matrix to mark direct road connections between pairs of cities. 2. Populate degree and adjacency matrix. For each road, U, V, in roads, increment the degree of both cities U and V since a road connects them. Update the adjacency matrix is _ connected to mark that a direct connection exists. 3. Calculate maximal network rank. Iterate over all possible pairs of cities, I, J, using two nested loops. Compute the network rank as the sum of their degrees, degree, I, plus degree, J. If the cities I and J are directly connected, subtract 1 from the rank to avoid double counting the shared road. Track the maximum network rank encountered during the iterations. 4. Return the result. Finally, return the highest computed network rank. Complexity. Time complexity, the algorithm runs in n squared, due to the nested loops over all city pairs. Space complexity, the space usage is n squared, for the adjacency matrix and n, for the degree array. This implementation is efficient for the problem's constraints and handles edge cases such as no roads or all cities being interconnected seamlessly. Here, we begin by defining the structure of our solution. First, we create an integer array called degree to keep track of the number of roads connected to each city. Alongside, we use a 2D Boolean array called isConnected to determine whether a direct road exists between any two cities. Next, we move on to populating these data structures. For each road in the input, we extract the two cities it connects, increment their respective degrees, and update the adjacency matrix to reflect that these cities are directly connected. These steps set the foundation for calculating the maximal network rank by giving us both the total connections for each city and the ability to check if two cities are directly linked. To calculate the maximal network rank, we iterate through all pairs of cities. For each pair, we add their degrees to get the total number of roads connected to both cities. If the two cities are directly connected, we subtract 1 from this total to avoid double counting their shared road. At each step, we update the max network rank variable to ensure it holds the highest rank encountered so far. After evaluating all city pairs, we simply return the maximum network rank as the result, completing our implementation. Here, we have a small network example to understand the solution step by step. The input specifies 4 cities labeled from 0 to 3, with roads connecting certain pairs of cities. To start, we initialize 2 data structures. The degree array will track the number of roads connected to each city, and the is_connected matrix will indicate whether there is a direct road between two cities. Initially, the degree array is set to 0 for all cities, and the is_connected matrix is filled with false. As we iterate through the roads, we update these structures. For example, the road 0, 1 increases the degree of both city 0 and city 1 by 1, and we mark is_connected 0, 1 and is_connected 1, 0 as true. By processing all roads in this manner, we end up with the updated degree array 2, 3, 1, 2, and an is_connected matrix that reflects the direct connections between cities. Now, we calculate the maximal network rank by comparing all pairs of cities. For each pair, I, j, the rank is determined by summing the degrees of the two cities and subtracting 1 if they are directly connected. For instance, for the pair 0, 1, the rank is degree 0 plus degree 1 equals 2 plus 3 equals 5, and we subtract 1 because they are directly connected, giving a rank of 4. We repeat this calculation for all pairs. For 0, 2, the rank is 3, as there is no direct connection. For 1, 3, the rank is 4, after subtracting 1 for the direct connection. After evaluating all pairs, the highest rank we find is 4. This becomes our result for this example. Next, we examine a simpler case where some cities are disconnected. Here, we have 3 cities and only one road connecting city 0 to city 1. Again, we initialize degree and is underscore connected. The degree array starts as 0, 0, 0, and the is underscore connected matrix is filled with false. When processing the road 0, 1, we increment the degrees of city 0 and city 1 to get 1, 1, 0, and we update the matrix to show a direct connection between these two cities. With this setup, we calculate the maximal network rank. For the pair 0, 1, the rank is degree 0 plus degree 1 equals 1 plus 1 equals 2, and subtracting 1 for the direct connection leaves us with a rank of 1. For the other pairs, such as 0, 2, and 1, 2, the rank is simply the sum of degrees, which is 1 in both cases. The maximal rank in this example is 1. The output for this example is 1, as the single road in the network limits the maximal rank. Now, let's consider a fully connected network where every city is directly connected to every other city. We have 4 cities and 6 roads connecting all pairs of cities. To start, we initialize the degree array and is underscore connected matrix. Through the updates, the degree array becomes 3, 3, 3, 3, since every city is connected to 3 others. Similarly, the is underscore connected matrix is updated to mark all possible direct connections between cities. With these data structures in place, we can calculate the maximal network rank. To compute the maximal network rank for this fully connected network, we evaluate all pairs of cities. Each pair, I, j, has a rank calculated as degree, I, plus degree, j, 1, where we subtract 1 because every pair is directly connected. For example, the rank of any pair, such as 0, 1, is 3 plus 3, 1 equals 5. Since all pairs yield the same rank of 5, the maximal rank in this case is 5. The output for this example is therefore 5. To analyze the time complexity of the solution for the maximal network rank problem, we start by breaking it into distinct steps. First, we initialize the degree array, which keeps track of the number of roads connected to each city. This involves creating a list of size n, requiring n time. Next, we set up the adjacency matrix, a two-dimensional array to record direct connections between cities. Since this matrix has dimensions of nxn, initializing it with false values takes n squared operations. Together, these initialization steps contribute n squared to the time complexity. After setup, we populate these structures by iterating over the given roads. For each road, we update the degree array and set the corresponding entries in the adjacency matrix. If there are m roads, this step takes m time. Since each road is processed just once, this part scales linearly with the number of roads. Combining these steps, the time complexity so far is n squared, from initialization and m, from processing the roads. The next step is calculating the maximal network rank. Here, we use a nested loop to iterate over all pairs of cities, considering only pairs where the first city's index is smaller than the second's. This results in n*n1/2 iterations, which simplifies to n squared. For each pair of cities, we compute the current rank based on the degree array and the adjacency matrix. Since these operations involve direct array accesses and a subtraction, they are constant time operations, or O1. Consequently, the entire nested loop contributes n squared to the time complexity. When we combine this with the earlier steps, the overall time complexity is dominated by the larger terms. If the number of roads, m, is much smaller than n squared, the complexity simplifies to n squared. However, when m approaches n squared, the additional term for processing roads makes the total complexity n squared plus m. This captures the worst-case scenario where both city pairs and roads are maximally dense. Now let's look at space complexity. The degree array, which stores the number of roads connected to each city, requires O(n) space since it has one entry for each city. The adjacency matrix, which tracks connectivity between city pairs, is an nxn matrix. Storing this matrix requires O(n)² space, as it contains an entry for every possible city pair. Additionally, we use a small number of auxiliary variables, like max_network_rank and loop indices, which take constant space, or O(1). When we sum these contributions, the overall space complexity is dominated by the adjacency matrix, resulting in O(n)². While the degree array and other variables contribute to the total usage, their impact is negligible compared to the quadratic growth of the adjacency matrix. Let's compare the optimized approach with a brute force or naive method. A brute force solution would involve generating all possible city pairs and explicitly counting the roads connected to each pair. This requires iterating over all city pairs, which is O(n)², and then iterating over all roads for each pair, which adds a factor of O(m). This results in a total time complexity of O(n)²*(m). On the other hand, the optimized approach avoids this repeated iteration over roads by pre-computing the degree array and adjacency matrix. This reduces the time complexity to O(n)² plus m, as we only iterate over the roads once and rely on pre-computed values for subsequent calculations. However, this optimization comes with a trade-off. The space complexity increases from O(m) in the brute force method, which only stores the roads list, to O(n)² in the optimized approach due to the adjacency matrix. This demonstrates how the current solution significantly improves time efficiency at the expense of higher space usage. Finally, let's analyze the best, average, and worst-case scenarios for this algorithm. In the best case, where there are no roads at all, m equals 0, the time complexity is dominated by the nested loop over city pairs, which is O(n)². For an average case, with a moderate number of roads, the complexity remains O(n)² plus m. In the worst case, when the number of roads approaches the maximum possible value of n*(n1/2), the time complexity is still O(n)² plus m. However, the constants involved in processing the adjacency matrix may make this scenario more computationally expensive. Mathematically, the nested loop over city pairs dominates the time complexity, contributing O(n)² iterations. Pre-computing the degree array and adjacency matrix adds linear and quadratic terms, but these do not exceed the asymptotic bounds set by the nested loop. Similarly, the adjacency matrix is the dominant factor in space complexity, contributing O(n)². This makes O(n)² plus m the justified worst-case time complexity, with a space complexity of O(n)². One common mistake is double counting edges when calculating the network rank. This happens when you forget to subtract one for a direct road between two cities, leading to inflated ranks, especially in dense graphs. The fix is straightforward. For each pair of cities, subtract one from the total if they are directly connected. Another mistake is inefficient computation for large inputs. If you use nested loops to calculate ranks for every pair of cities in a graph with thousands of nodes, the O(n)² complexity can become infeasible. To optimize, pre-compute the degree of each node and use hash sets to store direct connections, which can significantly reduce runtime. Finally, poorly handling edge cases is another issue. For example, graphs with no roads, fully connected graphs, or graphs with only a single road can break your solution if not explicitly addressed. Testing your solution against these scenarios ensures your implementation is robust and handles all inputs gracefully. Another potential pitfall is not accounting for bidirectional roads. In undirected graphs, roads work in both directions, so treating them as unidirectional can lead to incomplete rank calculations. To avoid this, use adjacency lists or sets that inherently treat connections as bidirectional. Another frequent error is confusing node indices with their degrees. This happens when you mix up the index of a node with the number of connections it has, especially when working with adjacency matrices or lists. These kinds of mix-ups lead to index errors or incorrect degree calculations. To avoid this, adopt clear variable names and double-check your indexing logic to ensure consistency throughout your implementation. Pre-computing node degrees and direct connections is a powerful optimization that speeds up algorithms significantly, especially for larger graphs. Recognizing patterns in the problem, such as adjacency matrices, node degrees, and rank calculations, can also help you design efficient solutions. When discussing your approach in an interview, it's important to highlight trade-offs. While brute force solutions are simpler to implement, they're often too slow for larger inputs, whereas optimized approaches are faster but may require more complex logic. Additionally, be prepared to discuss edge cases. Interviewers often use these scenarios, like empty graphs or densely connected graphs, to test how well your solution scales and handles unusual inputs. Showing that you've thought about these aspects demonstrates a thorough understanding of the problem. This problem shares concepts with several related graph problems, which are worth exploring to deepen your understanding. For example, LeetCode 997, Find the Town Judge, is another graph problem involving adjacency matrices or lists and degree calculations. LeetCode 1971, Find if Path Exists in Graph, focuses on connectivity between nodes, a foundational concept in graph theory. LeetCode 684, Redundant Connection, also deals with undirected graphs and involves edge handling, which is directly relevant. And of course, LeetCode 1615, Maximal Network Rank, ties all these concepts together, making it an excellent capstone problem for practicing graph-related algorithms. There are several alternative approaches to solving this problem, each with its own trade-offs. Using an adjacency matrix is a straightforward method to represent connections between nodes, but it can be memory-intensive for large graphs, requiring n² space. A more efficient option is using adjacency lists with hash sets. This approach stores neighbors in a compact way, pre-computes degrees, and tracks direct connections, making it faster and more memory efficient, especially for sparse graphs. Finally, you can use a degree-based calculation alone, without storing the full adjacency structure. This is the fastest approach, with a time complexity of n plus m, but it requires careful implementation to ensure correctness. Each method has its strengths, so the choice depends on the specific constraints and requirements of the problem you're solving. Great job! We've successfully solved the maximal network rank problem while exploring both brute force and optimized solutions. Remember to practice similar graph-based problems to strengthen your skills. Thanks for watching, and don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!